Welcome back to Applied Algebra and Trigonometry. We're going to be talking about trigonometric sum and difference formulas. As we discussed section 20.1, where it was an introduction to trigonometric identities, you learned that you can prove this identity to be true. Working with only one side, so we're not going around in circles, let's convert tangent of theta to sine of theta over cosine of theta, and then let's get rid of that complex fraction. Since we're dividing by a fraction, we multiply by its reciprocal. That means that those will cancel, leaving us with the true statement, cosine of theta equals the cosine of theta. Did I do that right, though? Or was it just wishful thinking on my part? Maybe I made an algebra mistake somewhere. You can check these trigonometric identities using your calculator. Simply pick a value for theta. Let's say theta equals 58 degrees. So I'm just going to put in 58 degrees wherever theta was in my original identity. When I plug it into the calculator on the left side, I get this. And on the right side, I get. So those values appear to be equal. Let's try checking another identity. Okay, looking at the sine of 75. Is it truly equal to the sine of 45 degrees times the cosine of 30 degrees plus the cosine of 45 degrees times the sine of 30 degrees? If we plug that all into our calculator, we get 0.9659203 on both sides. So yes, it does check. We have found an identity. Well, why would that be important? Because with no scientific calculator, you could evaluate that. And you could evaluate it exactly with none of this rounding that we have to do with the calculator if you remember special triangles. If you do not remember special triangles, I suggest you take a look at the PDF I posted in the content area called Trig Refresher. Here are two very special triangles. One is a 45-degree right triangle, or a 45-45-90 triangle, and a 30-60 right triangle, or a 30-60-90 triangle. In the first triangle, each side opposite of the 45-degree angle could have a measure of 1, and thus the hypotenuse would have a measure of the square root of 2. Another way to look at this is to let each side equal x, and then the hypotenuse will equal x times the square root of 2. If the side opposite the 30-degree angle is 1 in our second triangle, then the hypotenuse will be 2, and this other side, square root of 3. Or, if the side opposite of 30 is any number, then the hypotenuse will be 2 times that number, and the remaining side will be that number times the square root of 3. Notice that this angle of 45 degrees shows up in our identity above, and this angle of 30 degrees shows up in the identity as well. Why would we even think to look at 45 degrees and 30 degrees as part of an identity if we're trying to find the sine of 75 degrees? Well, 75 degrees does equal 45 degrees plus 30 degrees. So first let's figure out what the sine and the cosine of 45 degrees are. So let's see, sine is opposite. Opposite of 45 degrees is the side of length 1 over the hypotenuse, which has a length square root of 2. There's one problem with that. If you remember, we cannot have a square root in the denominator. That's not a standard way to express it. So we have to divide the numerator and the denominator by square root of 2 over square root of 2, giving us square root of 2 over 2. And that is what we are going to use as the value for the sine of 45 degrees. Remember that for a 45-45-90 triangle, the sine and the cosine have the same value. Now let's find the sine of 30 degrees, which would be the opposite, which is 1 over the hypotenuse. And the cosine of 30 degrees would be the adjacent over the hypotenuse. We're fine with radicals in the numerator, just not in the denominator. So the sine of 75 degrees equals the sine of 45 degrees, which is equal to this, square root of 2 over 2. Notice we have moved away from the trigonometric functions to these ratios. Okay, and then we have times the cosine of 30. Cosine of 30 right here. That's multiplied plus the cosine of 45 degrees found here, square root of 2 over 2, multiplied by the sine of 30 degrees, which we find there. Okay, and now we need to do the multiplications. Let's make a little more room, though. Okay, so we have the sine of 75 degrees equals the square root of 6 over 4 plus the square root of 2 over 4, or the square root of 6 plus the square root of 2 over 4, and we have the exact answer. If you want an approximate answer, plug it into your calculator and get 0.9659. Exactly what we had before. So this is your exact answer, and you can use this to check. All right, here's the identity that we just confirmed via the calculator. But let's take a closer look at this. This sine of 45 and cosine of 30 degrees, where did I get that from? Well, I got it from the fact that the sine of 75 degrees is equal to 45 degrees plus 30 degrees. I wonder if that would hold for any value. Could it be that the sine of some angle alpha plus some angle beta equals the sine of alpha times the cosine of beta plus the cosine of alpha times the sine of beta? The answer is yes. This is the formula for the sine of the sum of two angles. And if instead of adding a positive angle, we add a negative angle or subtract an angle, the only thing that changes is the sign. And this is often called the formula for the sine of the difference between two angles. Note that we have not proved these. We've not derived them. We have checked them to see that it is true for the given angle. We have examined the formulas, but go to your book for the derivation. The only problem with that is the derivation used by your book requires complex numbers, which we're going to get to next week, but not yet. This is again a case in which you should not get hung up with the names alpha and beta. Alpha is the first letter of the Greek alphabet, beta is the second, so think about them in position. So we have a first, an alpha, and a second, a beta. Then we take the sine of the first, multiply it by the cosine of the second, subtract the cosine of the first minus the sine of the second, second being the order within our parentheses there. Notice if you are taking the sine of a sum or the sine of a difference, the pattern is always sine, cosine, minus cosine, sine. The order of the angles listed does not change. I'm changing the order of the trigonometric functions. Why am I emphasizing this? Well, because we are about to do cosine functions. So let's move these out of the way just a little bit. The cosine of a sum of two angles gives us a different pattern. Instead of sine cosine, the first term is cosine times cosine. It is still cosine of alpha times the cosine of beta. I'm keeping the order of my angles the same. I'm just changing the trigonometric functions. So cosine alpha times cosine beta. Now, a sum, when you're taking a cosine, becomes a difference in the middle of the formula. So, and then you subtract sine alpha, sine beta. So cosine, cosine minus sine, sine. And the cosine of a difference of two angles follows a similar pattern to the sum. We have cosine alpha, cosine beta. The operation changes also from a subtraction, or difference, to a sum. And then we have sine alpha, sine beta. So let's try finding the cosine of 90 degrees. Well, let's draw a right triangle. And we'll label this 90 degrees. Now you see our problem. We cannot have two right angles in one triangle. We can get very, very, very close to 90 degrees, even closer. But what would it actually be if we made it to 90 degrees? Well, we can use this law of cosines to figure that out. Let's use the fact that 90 degrees is equal to 60 degrees plus 30 degrees. Why? Because we have our 30, 60, 90 right triangle, well, 30, 60, 90 triangle. 1, 2, square root of 3. Okay, but we need to use the formula first. Here's our alpha, here's our beta. So this is a sum. We will have cosine alpha times the cosine of beta. And I think we need a little more room. Okay, now we will have the sine of alpha times the sine of beta. And what are those values? Well, let's see. The sine of 60 degrees is square root of 3 over 2. The cosine of 60 degrees is 1 over 2. The sine of 30 degrees is 1 over 2. And the cosine of 30 degrees is the square root of 3 over 2. All right, so let's plug these in. Cosine of 60 degrees is 1/2. That's multiplied by the cosine of 30 degrees, which is the square root of 3 over 2. We're subtracting from that the sine of 60 degrees times the sine of 30 degrees. So in other words, we have square root of 3 over 4 minus the square root of 3 over 4, which is equal to 0, which means that the cosine of 90 degrees is equal to 0. Okay, a little more room, because now we need to talk about tangent. Now, tangent is different from sine and cosine when it comes to sums and differences of angles, because we're actually going to have a ratio in this formula of two angles right now. So it will be in the numerator the tangent of alpha plus the tangent of beta. And then in the denominator, it will be 1. We'll switch to subtraction, so 1 minus tan, or tan alpha, tan beta. If instead we are looking for the tangent of the difference between two angles, we will have a difference in the numerator. It will be a subtraction sign, and it will be divided by 1 plus tan. The tangent of alpha times the tangent of beta. Now you may see these two formulas combined into one. And if you see it that way, it will usually be written with the sum on top, the operations that involve the sum. So the tangent of alpha plus beta equals the tangent of alpha plus the tangent of beta divided by 1 minus the tangent of alpha, tangent of beta. And then beneath that, you will see the tangent of alpha minus beta equals the tangent of alpha minus the tangent of beta over 1 plus the tangent of alpha times the tangent of beta. And most math textbooks aren't as colorful as my videos, so it will usually all be written like this, usually in black. This video has been an introduction to these trigonometric formulas. The next video in this series will be some applications. What can you do with these things? We'll talk about that next.